Okay, we now have a thorough understanding of how graphs are transformed. So graphs of functions like shown here, or relations, or a relation like shown here. So any kind of equation, we now have a thorough understanding of how the graphs are transformed. However, as I've continued to make videos for the algebra course and videos for other courses, it's become apparent to me that I think it would be a really good idea if I laid out what I would call a default practice you should use for applying transformations, or for analyzing an equation that's already has the transformations applied, to see what transformations have been applied to it. Right? You don't know the transformation, so you want to look at the equation and break down what are the transformations. And I think this is important because, this really, I really noticed this when teaching the trigonometry course, and there's transformations applied to sinusoids. What I found was that, leaving how you can approach analyzing the transformations on the sinusoid, leaving that open-ended, I think ends up being kind of confusing. Because as we know, there's different ways you can apply flips to a graph. You can flip about the original x and y axis or the shifted x and y axis. For applying the same transformations, there's different routes you can follow. And don't get me wrong, it's good to understand all of those different routes. You want to fully understand how transformations are applied. However, I think giving you a default method for how to approach doing this is going to be helpful. So let's say we have a sinusoid, and the equation is, 3 sine minus 2x plus 5 minus 7. Okay, so looking at this, you want to analyze what are the transformations that have been applied. And so my motivation for making this video was that depending on the route you take, you could the sinusoid, the horizontal shift is called a phase shift, right? And depending on the route you take, that's going to change the way you view what the phase shift is. Because you could shift the sinusoid and then like flip about the original x-axis, so it gets confusing. But using this default method, the way you're going to look at it is you have the original sinusoid, and you can imagine it one of two ways. You either apply all of the non-translational transformations first. So all the stretching, shrinking about the x or y axis, any flipping, you apply all that first so that like the origin doesn't move, and then you apply any vertical and horizontal shifts, right? Or you can look at it from reverse. You could say you could shift it to what you would call its final position first, the original sine graph, and then apply all of the stretching, shrinking, flipping without moving this. With kind of like all that's happening about this new shifted position. That's what I would call the default way you want to analyze an equation to see the transformations that have been applied. We want to be able to, that's what I'm saying should be the default way you want to analyze an equation or a function to see the transformations that have been applied. You want to be able to read off, what is this distance? What is this distance? And then, about these origin points, how much has it been stretched horizontally? How much has it been stretched or shrunk vertically? Has it been flipped, etc.? Okay, and so to do it this way with this default method, what we're going to do is we want to rule out ever using any flips about the original x or y axis. Now, you can still do that if you haven't shifted it. Then if you're flipping, you're going to be flipping about the original x or y axis in that case. What I'm saying is, like, imagine that. So even this new transformed x and y axis, we can flip about. We've talked about how we can flip about these moved axes. Well, okay, imagine these moved axes at the origin, they're still there, right? We're flipping about those. We're never really flipping about these permanent x or y axes. Because once you start flipping about those, that's when it can get confusing on, well, what exactly is the phase shift? What are the horizontal and vertical shifts? Okay, and so, but everything I just said was based on this sinusoid, but that's all completely general for any equation or function. You know, all these rules we're about to talk about apply here and here and for whatever else. So, okay, the way you do this is, so how you analyze it this way is you're going to go to every variable and put it into this form. So, okay, we'll start with x, ignoring y for now. So, okay, I put a minus sign in front of the for this coefficient on purpose because this makes it the most general as possible. All right, you want to factor out what you need to factor out to get a positive 1 coefficient in front of the variable, in this case the x variable. Positive 1. I've mentioned in other videos, you know, in the trigonometry playlist that, you know, you could just factor it out to where you have a positive or negative 1, and that's fine. But the default method is, like, you can still do that and you can still analyze what's happening with the transformations. That's fine. But the default go-to method is you want to factor out what you need to factor out to get a positive 1 coefficient in front of the variable. So in that case, we want to factor out a minus 2. And that means we're left with x, and then will be minus 5/2. Okay, now we have it in a form where we can clearly read off all of the transformations, at least for about the x-axis. We've got a positive 1 coefficient in front of the x, and it's going to be plus or minus some constant that could be 0, and then a coefficient out front of all of that, a positive or negative coefficient. Okay, now let's do the same thing with the y variable. So if we add 7 to both sides, we'll get y plus 7 is equal to all of this, and then we can divide both sides by 3, and that will result in okay. So now we have both of the variables in the equation in a form where we can see the transformations applied about those axes. And again, it's from the sense of, it's like you shifted it, like here are the shifts: 5/2 in the positive direction, 7 in positive x direction, 7 in the negative y direction. And then we're at that new shifted position, and then with like the imaginary origin changed to that new shifted position, then we apply a scaling of negative 1/2 about the x-axis and a scaling of 3 about the y-axis. And so, but okay, well, what does the negative mean? That's like it's like you have the graph shifted to minus 7 or 5/2 minus 7, and there's been you imagine the x and y axis shifted with it, an imaginary x and y axis shifted with it, and here you flipped about that shifted y axis. So the graph, you start off shifting to, 5/2 minus 7, and so there's the sinusoid, right? And then you scaled about the x-axis by 1/2, so you shrunk it, and then you also flipped about this imaginary y-axis that's come with it. So it's flipped about this. It hasn't flipped about the original y-axis. We're not doing that with this default method. It's flipped about the transformed y-axis. And then it's also been scaled up about the y-axis by a factor of 3. Okay, and so, what's nice about this is that if you look here, it's tempting to say, oh, it's been shifted by 5 in the negative x direction. Yes, you can look at it that way from, if you understand transformations based on everything we've talked about previously, in the previous videos, you can look there. That does happen in a certain sense. There is at some point a shift by negative 5 in the horizontal direction. Like that's one route to getting to the final transformation. But if I bring in a graph of this function here, okay, here's the function. The way that we have it currently written, like this, is much more descriptive of the actual final transformation, which is why I'm saying to use this as the default method, because this is a sinusoid that has been shrunk by a factor of 2 about the x-axis, scaled up by a factor of 7 about the y-axis. It's been flipped about the y-axis, and there's not any original y-axis, but like flipped about its original origin y-axis, right? And then it's been shifted 5/2 and then down -7. Positive 5/2 down -7. That's descriptive of what the new sinusoid, right? So I had mentioned in some of the trigonometry videos that you could leave the minus, not factor out the minus sign, and so then you'd have a plus 5/2, and that's so 5/2 shifted 5/2 in the negative direction. That's fine, but then what ends up happening is you shift 5/2 in the negative direction, but then with the minus on the actual x variable, you flip about the original x-axis. And so now what happens then? Your final position of like the origin point is over here. So it's in the positive 5/2 direction. And that's not what it would, if you didn't factor out the negative, you can't see that clearly, right? And I wouldn't want to tell somebody that, I have a sinusoid here that's been shifted 5/2 in the negative direction, because to me that's not very clear. No, what's the final, you shrunk the sinusoid, you stretched it, you applied any flipping, and then where did you shift it to? That final molded form, you molded it into a new form, then where did you shift it to? Or you shifted it to a certain spot, and then you started molding it about its like new shifted center position. That's to me the default way you should be describing this, the most presentable way for describing transformations. But still, it's good to understand. I'm not saying that learning all of the different nuances isn't important. Everything we've done in the previous videos isn't important. It's good to understand and fully what's going on and how equations can be manipulated and transformed. But again, I'm saying this is the default way I would suggest you should look at transformations of graphs and equations. Okay, so let's take a look at an example with each of these equations. So here is x cubed plus y cubed is equal to 6xy. That's not a function, right? It fails the vertical line test. So, okay, let's say we want to, in the end, we want to have it shifted to the point 1, 2, positive 1, positive 2. So we come to every x variable and replace the x with x minus 1. We come to every y variable and replace it with y minus 2. Okay, now let's say we want to shrink about the x-axis by a factor of 2 and stretch about the y-axis by a factor of 3. And what's nice about doing it with this default technique is the order doesn't matter either. The order, the order doesn't matter if you fully understand what you're doing and of how the transformations work in general. Then the order doesn't matter because you inherently know what you're doing if you're flipping about the original x-axis, etc. So the order technically doesn't ever matter. But with this default method, you don't have to remember that, if you used any method, the order doesn't matter, but you have to remember that, okay, what did I just do? Did I flip about this the original x-axis or the transformed? You have to know exactly what you're doing. Here it kind of just is what it is. So, okay, we want to scale, what was it? Down about the x-axis by a factor of 2. So, yeah, you don't put the 2 out here. No, you need to apply this to it comes in here. You replace the x with x minus 1. Now you're multiplying that x minus 1 by, you want to scale the reciprocal of what you want to scale it. You want to scale it down by 2, so the reciprocal of 1/2 is 2. Okay, now we want to scale up about the y-axis by a factor of 3. Okay, so 6. What was it? 2. And there we go. Let's see what this graph looks like. Okay, so the red is the transformed graph. You can see that origin point, it shifted 1, 2, right? And then if we look at the loop here, we've scaled up about the y-axis by a factor of 3 and scaled down about the x-axis by a factor of 2. You can see it's kind of been smushed in, that factor of 2, and then stretched out. And it's been, you can see it's been like stretched a little bit more than it's been shrunk. Pretty cool, right? And again, you can clearly read all of that off from this form here. Okay, now let's look at an example with this function here. There's the untransformed graph. Now let's do a shift of -3 about the x-axis, +4 about the y-axis. So we're going to, the new origin is going to be -3, 4, and then we'll scale down about the y-axis by a factor of 2, up about the x-axis by a factor of 5, and then we'll flip about, let's say, the x-axis. So what did I just say here? We're going to, what was it? -2, 5, scale x by, I even forgot what I just said. So what was it? I don't know, whatever. So x up by 3, scale y down by 5, and then flip about x. All right, so we want to shift to the point +5 in the y, so y -5, and then we want to scale y down by 5 and flip about the x, so we want to put a -5 here. We're scaling down by 5, and then the minus sign goes, you know, if you want to flip about the x, you apply the minus sign to the y. Okay, now x, we are shifting by 2 in the negative direction, and then we want to apply a scale up by 3, so 1/3, okay, squared, and then just do the same thing to each of these x variables. Okay, let's see what this graph looks like. Okay, now this one's a little bit harder to see, but we've flipped about the x-axis, scaled down about the y. Okay, well, the new origin point you can see is at -2, 5. This, with the shrinking about the y-axis by a factor of 5, that lump kind of went down. You've flipped about the x-axis, and then scaled up about the x-axis by a factor of 3, so it's stretched out. You see how it's more stretched out. And there you go. So that's what I would suggest be your default method for applying transformations to equations or analyzing equations for transformations.